presentation. Thank you, everyone, for coming. So this is a summer school, and the summer is in full power. So I hope that today we will cover some things with regard to generative modeling and also, of course, drug discovery. And yeah, so a quick disclaimer. So wherever I can, I drop a reference to my paper. It's for very obvious reasons, because I know what I can tell about this paper, right? So this is not because I am a very modest person. So it's so this is the first disclaimer, and the second one is that we have like gazillions of papers, right? So whatever I drop here during this presentation and the next one, so it is just a pointer, right, for you, because after all, this is a summer school. It's not some exhaustive overview. It's really like to maybe spark some ideas. And today we are going to talk about generative modeling, Gen AI by science, so in particular in life sciences and molecular sciences. And thank you, Martin, for mentioning my book. It's indeed, it looks really good on the shelf, but it's also, I hope, very nice to read. So this is the first thing. All right, so today we have two parts. The first part will be more about like why we even bother, right? Why we are interested in doing whatever AI in drug discovery, and also in the first part we will talk about generative modeling in general. So I hope that after the first part, even though you are already probably convinced to do AI or to apply AI to drug discovery, but I hope that you will be reinforced at least, and also you will get something about generative modeling in general. So the first part will be somehow formal. We will drop some equations. I will use also blackboards. And in the second part, I hope that we can answer these questions like maybe what we want to do with AI, right? So maybe I will take some parts of the first presentation to the other one, but let's see. And if you have something really like urgent questions, so don't hesitate to ask, but I would prefer to keep questions at the end. Perfect. All right, so the first question I think that every researcher should answer is always the question about why, right? Why do we even bother? Why generative AI in life sciences, molecular sciences? So probably some of these numbers you may disagree or agree. It doesn't matter, it's like a ballpark. And in general, any R&D process in drug discovery takes something like, let's say, 5 to 10 years, right? So this is the standard statistics that everyone presents. And of course, in R&D, so we are interested in this first part, research. Like we are interested in target identification, validation. We want to understand, we want to have some scientific discovery, something that is interesting, such that we can carry on. And once we identify some interesting targets, maybe we figure out what kind of diseases, what kind of conditions. We also try to identify some drug candidates. After this research, and of course, if you are in academia, so the first part could be like infinity, right? You can do it forever. If you work for some company, of course, you are maybe more interested in the second part, so drug development. And here we want to identify lead compounds. We want to optimize them. So we are interested in some sort of screening, maybe some analysis, etc. Then, of course, we have in vitro studies and also in vivo studies. Once we finish this part, then we enter endless clinical trials. We keep our fingers crossed, and then that everything will be fine. And after another 10 years, maybe we can get to the market, right? So this is in general how it works, more or less. So where generative AI or AI can come in and what we can speed up, right? So one thing is that we can speed up research. By using AI, we can maybe get some data, we can process some data much faster, right? So there are like many companies in AI, generative AI, working on exactly this part, that we can maybe figure out some hits that we can move to R&D part. And then also in the R&D part, like more as drug development, I mean, we can even maybe further speed things up, right? Because maybe we can start analyzing data. We can process some data we have in much faster way. Maybe we can even help researchers and developers to actually look at some specific aspects. In my personal opinion, I think this part is the most interesting part for AI researchers, right? And many of these aspects we'll cover today. And what I want to highlight is that in the research part, very important are open databases. Right now we have many databases with millions of small molecules, at least thousands of proteins, and so on, so on. Another part that is very interesting is that actually we can understand molecular mechanisms, right? So I am a computer scientist. I am an AI person. And I'm always amazed by chemists because, you know, chemists look into things that we can't see with their eyes, and still people, they draw some conclusions from that. And very often there are hypotheses, actually, that, oh, okay, maybe it works this way. We have some molecular rules, let's say, and then this is something that we can get, right? And then we try to figure out, get some data, et cetera, et cetera. So now AI could be seen as so this is a very common perspective, that we try to use AI as a new tool, something similar to microscopes, right? That they help us to understand what's going on. And after that, we have this, as I said, drug development. So here we can use, for instance, de novo drug design and phenotypic profiling, right? We can try to figure out some mechanisms of actions and so on, based on different modalities. And here we don't talk only about molecular level, we can even look at some cell level, etc. As you can see, I don't mention anything about AI at this level because I think it's quite problematic, right? We can use maybe statistics and some sort of AI to process data, but after all, everything must go through human beings anyway, right? So I think that it's maybe, from my perspective, less interesting. Right. So this is the why. And also one thing I want to highlight is that if we go back and we look at numbers, so actually this story, I don't know, are you convinced by this story or not? This is maybe a good moment to ask. Who is convinced? Please raise your hand. All right, so it's like maybe 50–60% of people. It's actually quite interesting because many VCs are also not so convinced these days, right? So there was this recursion, even there is an invited speaker that will, I think, give his talk online from recursion, as I said. So they stock dropped like crazy. They laid off like 20% or 25% of people. The reason is that actually, if you look at that, these numbers, they look really cool. But in practice, very often, these big pharma companies, what they do, they just buy startups. Instead of spending even 3 years, they just go and say, all right, we are interested in this startup. So for them, this step boils down to a few months of figuring out the numbers and then just buying a startup and some drug candidate, okay? So the story is really compelling, but in practice, in real life, well, from the big pharma perspective, this whole process could be, as I said, few months, all right? So that's why many VCs these days, they're still excited about AI for drug discovery, but sometimes they're like, is it really like so lucrative and so on? I don't know. But this is something to keep in mind because we can do amazing stuff, but the reality is sometimes harsh. All right. So now what we can do with generative AI. So this is again to look maybe to zoom in into some of the tasks that are interesting. And here I highlighted a few. There are probably many more not covered here, but what I want to say is that, for instance, for target acquisition, so at the research level, so we can have, for instance, structure analysis. And so here we have these ideas like AlphaFold, Rosetta, and so on, right? All these methods. So what is the idea? The idea is that maybe AI, instead of going to crystallographers, we can just ask some AI tool to go from 2D to 3D, right? So the holy grail for many, many years. Now, somehow solved. Of course, still having crystallographers is good, but we can maybe get some first feeling within, let's say, hours, right? That we can get some results. Of course, data analysis. So this is like a huge piece of work to get enormous, gigantic databases available, to get your data from your wet labs to analyze and get something out of it, right? And here we can talk really about multiple different modalities, and we can also talk about different modalities combined into one method, right? Yesterday during poster sessions, there were such examples, for instance, how to get multiple modalities and get something out of it. So this is of course very, very important part. There are, even I think yesterday, the invited speaker said, I think that he had some startups at this level, right? Like only about analyzing targets. Then the second part, where I think there's most of the papers are somehow in this domain, I think, so in AI, I mean, for drug discoveries, so to how to identify hits and how to identify slash optimize leads, right? So we will have Hannes today that he will talk about also molecular docking, something that typically back in the day, like different, and still it's, I think, the reality. Medicinal chemists, they look into such models like there's this Schrödinger tool or some other tools that you can get your molecule, get your target, and see whether they fit or not, right? These days, actually, you can use AI to do that for you. It's much easier. There's even BioNeMo developed by a library developed by NVIDIA. So you can just download it, buy the GPUs, of course, and you can run these AI methods. And they do many things for you. So it's really like almost plug and play. Another part, and this is, I think, super interesting, is this de novo drug design. Because right now, we also have many, many good candidates for drugs. But of course, the point is to somehow optimize it such that you can patent your small molecule, and of course, be more specific, more selective, blah, 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 right? So all these aspects. So how we can design molecules for some given properties, more or less, right? So this is the point. So this is the task here. And then we have the next step. So once, let's say, we have our lead, we need to run through many, many points like pharmacokinetics, pharmacodynamics, toxicology, enzymatics, mechanism of action, and so on, so on, so on, right? So it's not only the point to find a molecule, we also want to analyze it, right? And maybe we can do something that, so we can use AI to do something to speed it up, to make it better, and so on, so on. All right? So I will try today to show you some examples in the second part here. And then there is another very interesting research line about, I will call it digital cells, patients, labs, whatever. So this is this general idea of going digital, right? And there is this dream of many people that before entering a wet lab, we can actually run almost all experiments, like millions of experiments in a digital lab with digital patients, with digital cells, all right? So in Europe especially, there is this very famous phrase about digital twins in general, right? And these digital twins we can use in life sciences, molecular science. All right, so this is something that's getting a lot of traction in the US. They like to call it virtual cells, virtual patients, right? But we are here now in Europe, so I talk about digital twins instead of virtual twins. All right, so this is the idea. And there is a very nice paper actually published very recently, I think from Recursion. It's Virtual Cells Predict, Explain, Discover. I highly recommend this paper. It's very well written. And they have this idea of how we can use AI, and they use these 3 categories. So about explaining, discovering, predicting. So explaining responses through some key mechanisms, discovering novel insight through lab in the loop, or predicting responses for therapies. And they have these very different stages. And here for you, I put this color such that you can see what kind of problems we can solve at these different levels. Of course, we are not going through all these now rows, but you can look it up. I shared slides, by the way, with Mateusz, so I think maybe it's already distributed. Right. So this is something very, very interesting because it shows that at least there are these 3 big categories of problems. So one approach is to develop specific models to solve specific problems, or we can go with these tools, methods that can solve these 3 different problems at once, right? Or can be used to solve them all. So now, of course, you can start publishing by looking at these different problems, or maybe getting startups, etc. But what I want to highlight it here is that why I'm using generative AI, by the way, as also some sort of an umbrella term, right? And in the next slide or a few slides, I will show why I look at it from this generative AI. And this is not only because of the hype, but it's really generative modeling is some sort of, I would say even like a philosophy of how to model things, all right? And it has, being able to generate new samples is a byproduct of generative modeling, okay? It's not something like the goal by itself. Right. Here is another example from the same paper. I really like it because it shows that the whole idea again, so we have some digital model, we can maybe generate hypotheses, we have some design, we are entering to a lab. Of course, robotics. By the way, I was quite amazed that in the Bay Area, robotics is super popular. Then analysis again in silico, some updates, and we close the loop. What I like here is, and why I also show this image, is actually about this arrow. Because the idea is very simple, and in AI, everyone thinks that, oh, right, so we have these models, they update themselves, etc., etc. But in the reality, it is not true. Okay, so I want you to keep it in mind. What we do in AI nowadays is that we take these crazy large data sets, we train some models, or we use some pre-trained model to fine-tune our model, and that's it. And we start using it. We deploy it, and that's all. This arrow is actually not there. If you ever heard about incremental learning or continual learning, we are unable to solve these problems in AI nowadays, all right? So something that we are, as human beings, so capable of, we listen to me, you don't forget what you did last day, right, or a few days ago. You still have this knowledge, and you update your brains somehow, and you proceed. In AI, we need to update these models, we need to take this model out of the loop, let's say out of some system, out of some environment. We have to go to a lab, we have to run, if you're at Meta, you can run thousands of GPUs, you update your model, and then you deploy back. right? There is no continual learning. And to me, this is the biggest problem in AI. So that's why I'm highlighting it here. It looks cool, we have this feedback loop, but in the reality, we don't have it yet. All right. So now it's the first moment that this is all about why and what we can solve. And I want to make this step back. After all, this is summer school. So I hope that you can learn something from next slides. This will be about generative modeling, all right? But to get some, like a moment, any question so far? Right, cool, perfect. So, well, please do have questions, right? It's not perfect that you don't have questions, but let's proceed. All right. Shameless self-advertisement. This is the second edition of my book, as Martin mentioned. It looks really great on the bookshelf, but it's, I hope, quite interesting. And for me, generative or Gen AI, it's actually generative modeling with deep neural networks. All right? And so what I said a few moments ago, and this will be the first moment that I will use the blackboard, is that to me, generative or Gen AI is not about generating per se. It's about really modeling, all right? And we'll have the next slide as well, but I want to highlight it already. Let's say that we have some random variables, x and y, right? Random variables because, well, we can assume that the world is somehow random, stochastic, etc., right? We can observe all variables. We can observe all atoms, so we assume there is some stochasticity. And oh, by the way, I should have asked earlier, how many of you have computer science background? Oh, wow, a lot. All right, cool. And mathematics? Nice. And chemistry? Cool. And biology? Oh, nice. Okay, cool, great. So we have different groups of folks, great. So just to mention, so we assume, what I mean by random variable is that we assume that there is some probability distribution, right? So we can say, and I am computer scientist, so I will use some notation quite loosely. So friends, mathematicians, please don't kill me, because I know that mathematicians are like quite pedantic, but we'll treat it like quite loosely, okay? So we have some probability distribution. This is the true distribution, whatever it means, that we get some data from that, let's say. And this symbol means that we can sample, let's say, it follows this distribution, right? There's also some distribution of py, and we can now say this is marginal distribution. Or it could be that it's actually conditional on x, right? Why I wrote it this way, because this is exactly one potential generative process. So here, and this is super simple, by the way, but it has really huge consequences, all right, for modeling. Oh, some technical issues, that's fine, okay. So it has very huge consequences for modeling purposes, all right? Because how many of you have heard about causality, right? Great. And so causality, and there is, by the way, the difference between causality people and generative people, in my opinion. So for generative people, it's something like, yeah, whatever, we define some generative process and we move on. For causality people, it's something like, hold on, we're interested in the true generative process. What does it mean? It means that if I tell you that this is the generative process here, someone can say that no, 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 the true generative process is the other way around. It's something that I need to have y because this y causes x. Right? This is the true causal structure. But in the end of the day, from both this, I know, I will do this. we get samples. If we follow this process and this process, mathematically speaking, in the end, we get this pair, a sample from X and Y, from some joint distribution, right? So we can say that generative modeling people are just more lazy because they just follow something that makes more, like it's easier for them to model in some way. But in general, this is all about having samples from this distribution, right? And now, why I'm saying that this generative modeling is philosophy in some sense, because it's really about answering this, how we generate data, how actually, if we look at the world around us, how this data come to us and what makes sense, all right? And so one thing that also helped me to understand a lot about modeling was if I have this generative process, or this generative process, doesn't matter, this generative process defined properly, then I can start looking to parts of these distributions and I can start model them, right? So this is, and if I have, for instance, in a generative process, if I have a loop, that let's say that I need to sample 3 variables to get the 4th one, but actually the 4th one is needed to generate the first one, it means that my generative process is incorrect, because generative process should be something that I can sample all variables in some order, all right? So this is the, like I would say, conceptual debugging if your model is correct or not, okay? So this is the main thing about generative models. And now, why I am saying that this is about deep neural networks, like in the title here of this slide, that's why this is either deep generative modeling or generative AI. By the way, I was thinking about calling it generative AI, but to me, generative AI is so cheesy that this deep generative modeling is, I think, nicer, but yeah, Gen AI is these days popular. Okay, anyway. So why neural networks? Because now we will actually look into this, that we will assume some model. So we will have some parameters here. Or I can be phi and psi. Or let's say psi and phi, whatever. And now we need to somehow model these distributions, right? In other words, we need to somehow predict parameters. And now this is the moment that mathematicians will be a bit angry at me, but these distributions, let's say that we have some Gaussian distribution. We assume that this is our Gaussian distribution. So what are the parameters of Gaussian distribution? Exactly. Mean and variance, right? So now, what we will do, well, maybe this was not the best example. Let's say this with y here. It would be easier to explain. Now we will say that this mean and variance are given by some neural network. It takes y, right? And so now it becomes a little bit, again, that mathematicians won't be super happy with me. Let's say that there are some weights in this neural network, and this neural network has weights that predict some parameters of a distribution, right? And so that's why I will use this term, this neural network parameterizes this distribution, right? Why parameterizes? Because it predicts parameters of this distribution, period. Okay? So this is how we use neural networks. We use neural networks to predict parameters of a distribution. All right? Now, to follow these introductory things, all right, I need to do that. Cool. I always feel so important when I have blackboards and I can do this. So now let's say that we have some data, right? We have some x and y and. Right. Let's assume for a second that they are IID data. What does it mean? It's called identically. All right. I will use larger. Identically. No, it's independently and identically distributed. Sorry, the other way around. Distributed. So it means that it's like flipping a coin, right? So every flip is an independent and identically distributed sample. Why? Because I have the same one single coin and I flip it all the time. Oh, cool, I'm there. Nice. So now it has very like real consequences, right? Because it means that if I look into my, oh, let's say not yet. If I look at my data, so this is x1, y2, y1, right? And because they are independently distributed, so it means that if I have I have a joint distribution, I have a product because they are independent, right? So independently means that if I have PAB, it's PA times PB. By the way, I'm really sorry for my handwriting. I think I should be forbidden from doing that, but still I do it. But I hope you can read what I'm trying to write here. All right. And we can write it straight away only because they're also identically. So it means that every single x and y comes from the same distribution px and y. All right? So having those two, and this is, again, if you think about this coin that I'm flipping virtually, so you can, I hope, buy that first they are identically because this is the same coin, the same distribution, and I do it independently. So having that, we can write this. Right. What is the property of probability? So one of the main things. Sorry? Yeah, someone is saying correctly. Yes, exactly. So when we sum over all variables, it sums to 1. And of course, it's always between 0 and 1. So we don't have negative probabilities. So what is the problem? Let's say n is 1 trillion. Why not? If I multiply something between 0 and 1 trillion times, exactly. It's like something 0.1 times 0.1 is 0.01, right? And so on, so on. So now, of course, now the computer scientist in me immediately screams that, hey, you will get not a number or 0, right? Or something. So it will be numerically very unstable. So what we can do, there is this magical function called logarit, right? So if we get logarit, we get sum instead of a product. And why computer scientists, and mathematicians actually too, I think, even though they always think that they are both everyone, so they won't agree. But everyone loves the logarit function for also another reason, that it doesn't change the optimal value, right, of some function. But also what it does is that it changes these pesky values between 0 and 1 to something that is now numerically tractable, because we will get values that are negative, but that are non-zero, basically. So now, if we, and now we said that we have models, so we have parameters. Oh, sorry, not here, here. Cool. So now we have almost like a ready algorithm without even thinking about it, like how we can look for parameter values, right? So now for given data, and this is, by the way, called the log likelihood function. By the way, what's the time? All right, I have 45 minutes, right? 45 minutes. I can do the dark date. Right, so this is the log likelihood function, right? So now if we want to find parameters, so this is our main question. What are the parameters? So we can solve basically this optimization problem that we try to maximize the log likelihood function of log P of data. All right? Sometimes people write it like, for instance, like that. And also, the name likelihood is actually really cool. Because if you think about it, it tells us the following. How likely my data were generated by model having parameters theta. All right? And now it's, to me, it was very beautiful when I first understood it. I read it at least 10 times and then finally understood it. Because now also math makes sense, because we want to maximize the likelihood. So it means that we are looking for such parameter values for which we can say that data are most likely to be generated by this model. Okay, so this is actually really cool. And now if you look at this one single blackboard, you have an algorithm for solving or looking for models. And everything follows math, right? So this is really follows statistics, right? So I haven't introduced something like, oh, mean squared errors or some hinge laws or something, you know, out of the blue. It really follows that. But you are smart folks, and probably you think, all right, but it's not concrete. There is nothing specific. You're just writing some mumbo jumbo on the blackboard and you're super excited. And so now everything will come from the fact that we have, oh, maybe I can use another color. I can mess up with you. Okay, perfect. So now, to be more concrete, we have to look into this. What is our model? And let's say that I will assume again Gaussian. And I will write like that to be, yeah, some covariance matrix. But I want to have one-dimensional, sorry. I will abuse a little bit this. So how do we, oh, now I'm going to use this chain. So cool. All right. So now we have Gaussian. How do you define Gaussian? It's like 1 divided by 2 pi variance. Please check if I'm correct. X to the power of 1. Correct? Cool. So now we are going back to the log likelihood function. So log of Gaussian, xn. Now we have constant, right? So this is constant is I do it on purpose. It's small because it's constant. It's not so important. And then we have 1, 2 sigma squared x minus mean squared. All right? Let's assume for a second that sigma is 1, right? So then we have really some constant. Oh, sorry, this was n here. All right. If now I write this, that there is this sum over n, and it's basically here. So anyone who worked with deep learning and implemented a single model, so you should know that what's the name of this loss. I think someone whispers very like quietly this. Perfect, perfect. This is MSE, right? And now I hope that you're getting this excitement that I got when I first saw it, because now it turns out that actually, oh, these losses, they actually follow some distributions. And everything is the log likelihood, not everything, but many things are the log likelihood, they follow from the log likelihood function, right? Now I'm running out of blackboards. So we need to erase something. Oh, perfect. Amazing, thanks. Right. So now, what if we take Bernoulli distribution? So we have and some theta. Oh, sorry. Right? What is the Bernoulli distribution? Bernoulli distribution is when we have binary random variables. All right? If we now take the log of that, oh, sorry. How do we call it in deep learning? Exactly. And even binary cross entropy, right? If we take the categorical distribution, we get the cross entropy loss. All right? So now we can see basically we have a general prescription called the log likelihood function. And then depending on what kind of distribution we take, we can derive the correct loss. All right? And the funny part is that basically there are 3 main losses because we use 3 main distributions in deep learning or in machine learning or AI. It's Bernoulli distribution, categorical distribution, and Gaussian distribution. All right? There are, of course, many more. There are like logistic distribution or discretized logistics distribution, but these are the main 3 distributions that we use. All right? Is it clear? Perfect. All right, we can move on with the slides now. We can go back. Perfect. Let this slide sing with you. You know where to find it? Okay, perfect. So now it's this, like, let's say, this triangle. And this triangle will be quite useful for our story to tell, all right? But this is exactly what we said. So we have the joint distribution, and we have, let's say, this conditional and marginal distribution. And then by having 2 rules in the probability theory, the product rule or the sum rule, having either this distribution or those two, we can go on this triangle because they are all the same, right? But of course, it matters how we approach the modeling task. Are we really interested in modeling the marginal or the conditional or the joint straight away? And now here is why, to me, it's, I hope now getting clearer and clearer why I think about generative modeling, not in terms of sampling, aka generating, but in terms of this probabilistic modeling, right? Because to me, it's really about getting this distribution. To me, this is the one that I'm interested in. If I have that, I can model my reality, all right? And then, of course, I can sample. It doesn't mean, at the same time, that sampling or generating is bad. It's actually, it could be very useful, but this is our goal, not sampling itself. And now, depending on what we are interested in, we will look at different distributions. All right, so now let's move on. So now we want to solve this problem of how to model these different distributions, all right? The first approach that, in my opinion, is the most straightforward, but interestingly, I think in generative modeling field, this was not the most popular approach for many years. These days, you can say it's everywhere. It's called autoregressive modeling. Do you know why it's everywhere these days? Or what's the name? Sorry? Exactly, and LLMs, right? Because this is exactly how we model these huge, large language models. Because what we do, we use the product rule from the previous slide, so this one, right? So every joint distribution we can so-called factorize, we can represent as conditionals, the multiplication of conditionals. So let's say that X is our text, and now we can take it to the extreme case that we just simply take the first word or the first token, then we multiply it by the probability of the first token given the second, the second token given the first one, times the third given the first and second, and so on and so on and so on. All right? And why I said that it was not very popular in the generative modeling community for many years, because it's a little bit like almost stupid if you think about it. It's like, yeah, I have to somehow model all these long-range dependencies, because if I have 1 million tokens, like the last conditional is dependent on 1 million minus 1 tokens, right? And now from the modeling perspective, the question is how I can do that I really model these long-range dependencies, all right? You may say, let's cut it in half, or let's take the last 10 tokens, right? Now, here I will be maybe a little bit with causality, folks, because this will be definitely something very far from this true causal structure, right? And if I can keep all these 1 million minus 1 tokens as my condition, so if I have, I will use, I always use this mathematical term, if we have large enough number of observations, whatever it means. So at least if I have really a lot of data, I can mimic the generative process. Even though it's not causal, I can mimic it. Because these conditional distributions, they will start figuring out all these hierarchical correlations. They will start resembling this, let's say, causal structure in some sense, or at least the generative process, okay? So the whole point in this kind of modeling is actually how we can model long-range dependencies, right? But from the generative modeling perspective, this is actually the most straightforward approach. Why? Because it defines this beautiful generative process. First sample the first token, then sample the second one given the first one, then sample the third one given the first and the second, and so on and so on. So it's super clear, right? But now the question is what kind of neural networks we can use. And here I use this figure where I use this term causal conv1D. So this was the biggest breakthrough in deep generative modeling, when people proposed to use convolutional neural networks for, let's say, 1D sequences, right? And what it is very simple. If you're familiar with convolutions, wait, I have blackboards. I can use them. Let's say we have a sequence. Convolutional layers, they are these shifting windows, right? They go from, let's say, the left to the right. And let's say I'm at this token, and I have a kernel of size 3. So I have 3 weights. And now it works that, let's say, x1, or it's 1, third, w1, w2, w3. So now the output of that is w1 times x1 plus w2 times x2 plus w3 times x3. Okay? So this is what we have. It's super simple, right? And now we shift this to the right. How we can use that for autoregressive models? Because from the autoregressive perspective, this is of course wrong. Why this is wrong? Exactly. We can look at that. Where is the red one? We can look here because it's the next token that we don't have yet. From the generative perspective, it's nonsensical, right? Even further, if we apply it to tokens themselves, we need to remember that what a neural network gives us, let's say previous tokens, it gives us the parameter of a distribution for that given token at this point, right? So we can have access to that either. Is it clear? We can provide parameters for a distribution to generate a given token if you look at this token, right? So we have to exclude that as well. So that's why it's like lower than this t. Or what is the notation here? D, sorry. And this is the whole point of these causal convolutions. So we don't have this for in causal causal convolutions and this. And of course now we can make it larger, this kernel, right? But why it's cool, why convolutional layers are cool? Because they are implemented in CUDA. And we can very easily use them. And we can, even though they are like, for training, even though we have full sequences, we can process them in some sense in one forward pass, right? So this is super efficient. We don't need to write some pesky for loops for training. We just have our code, one single model, the loss function, go. Another thing, but of course now you can say that what do we do in, this is the 4, 5. In convolutions, if we are at the first token, of course we need to pad it, right? So we need to add zeros. And now I said, hey, this is super important because this is the whole point of modeling. So now if I have 1 million tokens, so I need to pad it with 1 million tokens minus 1, or actually 1 million tokens of zeros, right? To have this one single forward pass. So it sucks, let's be honest. Because then suddenly we deal with gigantic model. So how we can overcome that? Well, there is a very nice way of doing it. We can start stacking these causal layers, right? And then even further, we can do dilation, so we can have these gaps in between. And by having that, we can like enlarge how it's called, the exactly, or the context, like because I was thinking about these LLMs, right? In this context, we can enlarge it like crazy. And so this is the example here. So we have this causal convolution stacked, we have this dilation. So take a look. This output or these parameters for this div token, we look at the whole history here already. And actually causal convolutional layers are very powerful, yes? Yes, sure, we still need to path, right? Yes, yes, exactly. All right, I think I have to speed up because I'm getting too excited with the blackboard. Yeah, okay, we have half an hour, I should be fine. Okay. So now, and of course, the new architectures are transformers, and I'm going to mention them in a second. But here's again this example. And by the way, oh, this is important, I didn't mention. The first causal conv1d cannot look at the current token, but once we process everything, it's actually fine to process this current latent or hidden. Okay, but still we cannot look into the future, that's for sure. Cool. All right. I really love this example. So this is like autoregressive models can be parts of other models. This is important to realize because they model, let's look at it here. We can always put some conditioning here, and then all these distributions are conditions by the same variable, okay? So we can do that. So now, for instance, autoregressive models were used for audio processing, so-called vocoders. And here, this was from, I think, DeepMind. So here we have this encoder. It takes some audio. It processes it. It generates some encoding or some latent. And then we have an autoencoder decoder that takes this conditioning and predicts what is this sound. And then we have this generative model, and they used this autoregressive model also as a prior for this latent codes, right? So why I'm showing you this example, because this autoregressive model is used in two points. One as a prior over some latent variables, and then as a decoder for generating audio, right? Cool. Right. Then we can have, oh, not autoencoders, they're autoregressive models, sorry. So now we can also use transformers. And transformers are not necessarily only for autoregressive models. There are some general architectures. And they are actually extremely simple, but yet very powerful. So how do they work? So they use something that is called this attention or self-attention mechanism, right? And basically what we have some tokens, we embed these tokens, and then we have these transformer blocks that consist of some a sequence of self-attention, layer norms, small MLPs, and layer norms. By the way, these layer norms are extremely important for one particular reason, to keep all the gradients during training at bay, that they don't explode, right? Because if you look at this, if you are familiar a little bit with math, so you can very quickly realize that they can, without these layer norms, these numbers can grow and grow and grow and grow, and they will explode. But by applying the layer norm, we always squash them. So when we calculate gradients back, we don't have this explosive effect. Right. So as you can see, so there are residual connections, multi-head attention, layer norm, MLP, and layer norm. So the important part is actually the attention mechanism. An attention mechanism is defined in this, I would say, quite simple way. So we take our axis, so our inputs, we have nice diagram from Simon Prince's book, a very good one, by the way. I highly recommend it. And so we have some input. We just use matrix multiplication everywhere, nothing fancy, so linear layers. So we take this input, we calculate something that is called queries, keys, and values. We multiply queries and keys together, we get the attention matrix, and then we apply the softmax function, and we again multiply these two matrices together. And by having these very simple linear layers, you can calculate something that is very powerful. Why? Because this attention matrix, or this attention weights, you define how you look at given input tokens. Right? So now we can apply some mask that will exclude, for instance, looking to the future tokens. Right? And also the attention weight, attention matrix, you can think of it as some sort of defining a graph that indicates which tokens are connecting to which tokens. Right? Are you familiar with how it's called? The incidence matrix in graphs, right? So this is like which node is connected to which node. And because we apply this softmax layer-wise, so we indicate, and softmax is between 0 and 1, right? It sums to 1, it's between 0 and 1. So you can say that this softmax gives us this soft incidence matrix. It shows that, oh, this node is connected with weight 0.25 to this node, or 0.7 to this node, or 0.05 to this node, right? Yeah? Is there a question? No, all right. Cool, so this is the main thing from transformers. And now we can also have this, as I said, so we can have so-called encoders that we don't have any mask here, or we can have this causal mask that we ensure that we don't look into the future tokens. And then we can use that for autoregressive models. And this is exactly the idea behind LLMs. We have this together with this big factorized model. If we want to sample, of course, we need to have a for loop. We initialize everything with some, I don't know, empty tokens. We just have a big for loop that we generate the first one. We plug it back, apply again a forward pass. We generate the second token, and so on. All right. We can also, of course, combine those transformers to have some conditioning, but this is, let's say, secondary. Cool. Any question about it? Because I will look into now completely different way of thinking. All right, perfect. So now there's another class of models called normalizing flows, or flow-based models. And here the idea is quite mathematical, super beautiful, mathematically speaking, but also it is pretty constrained. That's why it's maybe not so popular these days, but I think it's very important to mention, because if you have some lower dimensional problems, I think normalizing flows are really good for that. For instance, physicists love that, models. They use it like almost everywhere they can. Right, so what is the idea? The idea is actually maybe the best to look at this simple diagram or scheme. So let's imagine that we have some very simple distribution, right? Like standard Gaussian. And now we want to get to this complicated multimodal distribution of our data, or the real distribution, whatever it means, right? So now the question is there some process that transforms this simple distribution into this very complicated one, right? And now I will give you a very simple analogy. Let's imagine that we have a pile of sand. And for some weird reason, this pile of sand is standard Gaussian, right? So with this infinite tails. But now imagine that I take my two hands, and I let's say this is on this 2D plane. So I have also points, some x's that denote my observed data, right? So now my point is to take this pile of sand and put like appropriate amount of this sand at these places where these x's are, right? Is it doable? Of course, because I look at this axis and I just start moving this sand, correct? And then let's say I'm so like correct that I put the proper amounts where there are many axes and so on, right? Do you agree that it's possible? Perfect. Now let's say someone recorded me and now played it in the reverse, right, order. So now you see that actually my hands start going again to this standard Gaussian, right? Voila, you know what is normalizing flow. Because the normalizing flow is about defining something that is called this invertible transformation. So something that we can move our hands and we can play in reverse such that we see all the steps and we don't lose a single piece of this sand pile. So this is something that's called, mathematically speaking, beautiful word, bijective transformation, something that is invertible. I can always invert it. So if we can define this invertible transformation f, or this sequence of these invertible transformations, we can always go from one distribution to the other. But now there are some issues, of course. So the first one is that we need to come up with that, these transformations. Second is that we need to think about some neural nets, because why not, right? There are powerful transformations. So we need to think what kind of neural networks and how to ensure that they are invertible. This is the first point. And mathematically speaking, there is something that is called the change of variables rule that says that I can transform one distribution to the other using invertible transformations, but I need to ensure that the volume of this distribution is preserved. So if I suddenly, you can see, like for instance, imagine that you have a square, and now I have an invertible transformation that this square is squashed somehow. It's, for instance, smaller. Because of the oddity of continuous variables, I can think of an invertible transformation, so this square, I can revert back. But now, to preserve the volume of that, I need to multiply it by the new volume. So this is the idea. And this is called the Jacobian. And now, we have two tasks if we want to apply this idea. First, we need to come up with these invertible transformations that are somehow, like, computable using neural networks. And second is that for these transformations, this Jacobian is tractable, because the Jacobian is the determinant of a big matrix, right? So now, if you are familiar with calculating determinants, they are not very simple to be calculated. So we need to come up with something that is easy to do. And here is again this a different representation, a 2D example. And also, here is actually a very nice representation, because now if we think about these steps as some sequence of transformations, aka a neural network, let's say. So in the forward pass, we always need to output the next point, or the transformed point, and the log of the determinant of the Jacobian, right? So this is our forward pass. Then in the backward, we collect all of them and calculate the gradient. The good thing I want to highlight is that we have the exact form for the log likelihood function, no approximations here, right? So we can calculate the log likelihood function. That's why physicists love this idea so much. Perfect. And now here is the idea of a neural network that is first invertible and second, it is tractable. And the representation with these blocks may look like very confusing, but actually it's extremely simple. Maybe it's even simpler to look at the math here. So we have the original input, and we divide it into two parts. The first part is left untouched. We don't transform it at all. Then the second part, we transform with two neural networks. The first one is exponentiated. So in general, this one, it's some scaling factor. So we scale the second part, and we translate the second part somehow. This is another neural network. These two are neural networks. And we just add them. So by having that, this affine transformation, we can process the whole part. And this is here denoted. Now, the good thing is that this is invertible, because the first part is untouched. So we just write it back. And then these transformations we can revert. So the first point is there. It is invertible, right? You may immediately ask, because you are smart people, you can immediately ask, so if I keep this untouched, so how it is so powerful, right? The trick is that after that step, we use another invertible transformation. So we just swap these two parts. And then we stack another layer. So having this layer called coupling layer, then inversion, let's say permutation, and then we have another coupling layer. In these three steps, we process the whole input. And how this swapping is invertible, I think I don't need to convince you, right? If this is fixed, that I always swap two parts of a vector, I can always just swap it back, as long as I know how I swap in the first place. The beautiful idea behind this is that actually the Jacobian is very simple to calculate. Because the Jacobian is a matrix where we calculate derivatives with respect to variables. So here we will have, if we look at that, so if we calculate this with respect to derivative with respect to z lower than d, so we have the identity. If we calculate derivative with respect to all these larger than d, so we will have zeros. And if we look at the other part here, so we have neural networks that are dependent on this z smaller than d, and this will be also, this is larger than d. If we look at the Jacobian, we have this super weird part that is very hard to calculate. And here we have just the exp of this S neural network. And because we calculate the determinant, and this is lower triangular matrix, so we have this property that the determinant of the lower triangular matrices is just as the product of the diagonal. So if you don't follow, just trust me, please look it up later. But this is super cool, because now the determinant of the Jacobian is just the product of exponents. And because we have this exponent, now it's like why we use the exponent, is that exponent is of sum of these neural nets. And if we now look back these few slides, if we take the logarithm of the log likelihood function, sorry, so then we'll have log of this Q0 plus sum over this, logarithm of these guys, and because we have exp, so it cancels out, all right? So all these very particular choices now come together and we get quite nice framework. All right, now I have to speed up a little bit because I'm probably out of time. Yes, I have 10 minutes. But you were late 5 minutes, that's why. All right. So now about latent verbals and latent verbal models. So here is, I would say, latent verbal models are like degenerative models in some sense, because they assume this very nice generative process. They assume that we have some latent factors of some highly complicated data, like MNIST, and then we have these Z's. So there are something that is in this data. You can think of it as some codes, as some maybe compressed information, as maybe some factors like determine how thick these digits are, what kind of digits, etc., etc. We don't know. They are latent. But we assume that they exist. And now for these given factors, we can go back. We have some transformation that takes these low-dimensional factors, and they give us these high-dimensional objects, right, like images or something else. And in this class of models, we distinguish GANs and VAEs. And first, GANs, very quickly. So they assume that this transformation, they are called generators. We have some distribution over, very simple distribution over its latent variables, and we have some generators. And to train it, because now we can train them by using the log likelihood function directly, we can do that, but it could be quite problematic. So Ian Goodfellow and others, they suggested this, like formulating a game. So this game is that we introduce another neural network that is called a discriminator that takes this x, whatever x, and it determines whether this is like real x or this is a fake x that was generated by our generative network. And now we start playing it, and we have these two neural networks, a generator and discriminator, and we want to train them at the same time. And of course, the discriminator has this very simple goal, to really say whether this is real or fake. And this generator has another goal, to actually fool this discriminator in such a way that these data start looking like real points. And the problem is to solve this min-max problem. It is actually, if you look at it, it looks like, I don't know if this x is minus squared, maybe yes. It is something like we have this, we take data, and we take the discriminator, and then we take this latent point, so fake data, we generate, let's say, some objects that resemble real objects, and we have this. This is really cool for many things, like many reasons. For instance, one is that you can say that the whole loss function is learnable, every single aspect is learnable, but at the same time, this is the min-max problem, and it is extremely hard to solve. That's why I'm not a big fan of GANs myself. However, I really appreciate how well they work and how powerful they can be. But for instance, when I implemented them for the book, I actually implemented GANs 2 times in my life, and that's it. So first time when I had some idea many years ago, it didn't work out. And the second one for the book, and then I had this huge issue to train GANs, and I checked my code 3 zillion of times, and then I realized that, oh, I need to play with the learning rate. And then it was like when I changed the learning rate a little bit, it started working out of the blue. And then so I said, oh yeah, that's why I don't like GANs. That was the reason. And now, the second idea that I actually love is about the variational autoencoders. And why I love this idea is the following. So now we assume that we go from this latent space to this observable space, and we also have some other distribution that actually goes back. So now, variational autoencoders, also called VAEs, they are in some sense super broad class of models, depending on what kind of queue and so what kind of encoder and decoder we use. But if you look at it, and now if you think that, oh, if I start looking into invertible transformations, and I keep the dimensionality the same, we're going back to normalizing flows. So this is in some sense a generalization of that, right? And this is one single slide, very briefly, but there are the key points of VAEs. So we have this very well-defined generative process. We sample latent variables, and then we sample observable variables. And to go back to the latent space, we have something that we call variational posterior or an encoder. To make the whole game nicely learnable, we can use something that is called a reparameterization trick to lower the gradient variance. I'm not delving too much into the details, but just trust me, please. And so the reparameterization trick is very simple. If we take Gaussian, every single Gaussian could be represented as the mean plus standard scaled standard noise, right? By using this one single line, you can generate whatever samples from a Gaussian for these parameters. And now it's super cool because if we calculate, take a look, for given x, we try to calculate z. So this mean and this standard deviation, we have given by some neural network, right? So now we can start learning how to go from x to z. And moreover, we have this one single line that is very easy to calculate and backpropagate through, all right? Because we don't backpropagate through stochastic process, we backpropagate through neural network that is deterministic. And how we can train it? Using an approximation to the log likelihood function called the evidence lower bound. And how we can derive it, so here's how we do that. So we take the logarithm of this integral, so the sum rule, p of x given z times p of z. Then we introduce these variational posteriors, so we multiply by 1 here, right? Q divided by q. Then we get with the logarithm inside the integral, so we get the lower bound, Jensen's inequality. And by playing around, we just get the first part, so reconstruction error and the regularization term. So the Kullback-Leibler between the variational posterior and the so-called prior, all right? So this is like, I'm speeding up a little bit, but this is actually super simple derivation, right? So I saw it first in slides given by Zubin Garamani from Cambridge, and I was like, wow, this is actually not so complicated. The only thing you need to know is Jensen's inequality, and you need to know the trick that allows you to multiply anything by 1, right? By the way, I had a colleague during my studies that she always used this trick, and she always got the maximum of points for whatever tasks, but she was like brilliant. She always used that. Cool. And so these are VAEs in a nutshell. And here is something that is super powerful these days called diffusion models, right? So I have to look at the time because maybe I can bring it to the next part and we can start with that. I have a few slides and then I can proceed. Is it fine with you? Perfect. So some questions before we...
I think so. We still have 5 minutes for some questions because we started late and we can start from diffusion models the next session. Yeah. Are there any questions from the audience? Nathan?
Yes. Oh, wow.
Would be hard.
Yes, it will be hard.
Is there any future for GANs, and why not?
Sorry again?
Is there
a future?
Yes.
Oh yeah, actually, so this is funny. Thank you for this question. The question is there any future for GANs? I think definitely yes. So first of all, I know that there are some papers these days about actually combining GANs and diffusion models. And these approaches are pretty powerful. The second thing is that actually there's one caveat that I didn't mention about the log likelihood function based approaches here, is that sometimes, like in general, the log likelihood function is not the best because the log likelihood function actually looks at, I have one point and how my model fits that point. But what is better is actually to look maybe at distributions as a whole. And GANs actually do that because they try to move the probability mass at this like distributions in general. I remember yesterday there was this poster about Wasserstein distance. So for instance, Wasserstein distance is actually that it does it, like it moves the whole distribution. Optimal transport, also these things, all these ideas are actually connected. And many ideas in the GANs, let's say, space. So they use Wasserstein metric, right? Wasserstein GAN, and all these ideas. So I think that there is a lot of future. And also, even though that I failed at training these GANs easily. But once you know some tricks, I think that they are also not so hard to train these days. So yeah, I think that for sure. Thanks. This is a very good question.
Yeah, Jakub, I will also prevent GANs from you. I think your problem was basically from the standard problems, because GANs are secretly energy-based models. So we have exactly the same problems, but they are beautiful and powerful in theory.
Yeah, that's a good point. I will have, by the way, after diffusion, there are like 2 slides about energy-based models.
Cool,
so
the best ones.
Yes. Cool, thanks. Any other question before we go? Perfect. All right.
So
Thank
we
you.
are ready for the coffee break, I guess, and we'll meet.
Welcome back after some coffee break. And so now I'm going to say these few words about modeling, and then we'll focus on applications. And also, then maybe we can have some discussion. All right? So right now, here we have this extremely popular these days and extremely powerful models called diffusion models. And I like to look at diffusion models from this perspective of VAEs. So in VAEs, we have these latent variables, and now imagine that we have thousands of latent layers, all right? And we give, and every single latent level is, the dimensionality is the same as the original objects. And now imagine that we define this process in a very particular way, namely from one step to the other, one level to the other level, we add a little bit of Gaussian noise, right? So like here we have this example, we have a photo of a cat, and now with every single step we add more and more noise. That eventually in the end we have pure Gaussian noise, right? So in VAEs, these variational posteriors, we can say that we want to destroy data completely, right? And then in this called forward diffusion process, in the backward diffusion process, we try to recover all the results. Again, this is like very generative way of thinking, right? Because now we, of course, in the how we generate data, we start with pure noise, and step by step we try to figure out what are the details. All right? So this is the general idea of diffusion diffusion-based models. Like here will be a little bit of math again, but just trust me, okay? That this hopefully there are no errors. But also this is something that some points that I want you to remember from that slides. So also we can say that if we think of it as hierarchical VAE, that every single level is a latent variable, so we can of course again calculate the elbow. So we have this many steps, and we have the elbow. All right? And this is an interesting fact. It was published in 2015. I think Jascha Sol-Dixon, he presented that at some workshop in 2016, and I listened to him at NeurIPS. I think it was in Barcelona back then. So this is, he presented that in 2000. I listened to him in 2016 in person, and I remember that when I came out from his talk, I was like, this is super cool. I don't get it, but it's super cool. And then it took people around, I think, few years, 4 or something, that Jonathan Ho, 4 or 5, that Jonathan Ho actually turned it into a very powerful model. But this is also a nice story in research that they published it for 5 years. It was super niche. No one knew this paper. And then after 5 years, big boom, and now everyone uses that, all right? So if you have some idea you believe in, don't give up. Maybe one day it will be great. So, all right, so in diffusion models, so we have this, we have very nice properties. So here I need to use the blackboard again for a second. So we have this, that if we go from zt minus 1 to zt, this is Gaussian. And this is very particular Gaussian, that we have some scaling factor, and then we have minus 1, of course. And then we have this covariance matrix that is diagonal, right? So as you can see again, because I just went through it without maybe explaining. So if we go, if this beta t, let's say, goes to 1, so this will become 0, and this will be just the identity matrix, right? I hope you can see it, right? From one step to the other. Another thing is that if we write it like, let's say, this is A, T, and this is, let's say, BT. So sample from that, again, the reparametrization trick. Square root of that, some epsilon, right? So as you can see, this is a linear model, right? Or a linear transformation, right? And it is also Gaussian. So actually what we have, it's called linear model. I can give my pinky that every single person in this room knows very well one model, right? Do you know what I mean? Have you ever heard about principal component analysis, aka PCA, right? This is a linear Gaussian model, if you look at it from the probabilistic perspective. What does it mean? It means that for linear Gaussian models, you can play around with probabilities. Like having this, if this is a linear Gaussian model, you can calculate this in closed form, in analytical form. You can always play around. You can change conditionings, etc., right, for linear Gaussian models. And we can use these facts. And we can calculate very useful distributions. First, we can calculate distribution of zt given not zt minus 1, but x. So in other words, if you think about it, like this diffusion process is like adding a little bit like super small steps. And this is like this being this random walk, right, way. But instead of that, you can say, instead of making trillion of steps, I can do one big step from x to zt. And this is exactly what it tells us. You can do that by going from x to zt directly. And you can calculate it in a closed form. But also, because it's linear Gaussian model, we can calculate the zt for given zt plus 1 and x. This is a little bit more complicated, but it looks only complicated. Everything is linear here. Okay? So in other words, we can also calculate this distribution. Okay? If you don't see it for now, trust me. Homework, you can check it out. It's really true. So now we have, instead of working with this distribution, we can actually work with these two distributions. Why is this important? Because if we look at the elbow that is written like that, calculating it for thousands of steps is just simply infeasible. There is no computer that could keep everything in the memory. But because we learn using stochastic gradient descent, by the way, this is always a very good trick. If you train with stochastic gradient descent, if you have some objective, you can also pick some stochastic or randomly, you can pick some components and optimize them, because let's say in the infinity, because of stochastic gradient descent is stochastic, and then you pick something stochastically, so on average you are optimizing everything properly. So instead of doing that, there is this one huge step that I made because I don't want to make this about diffusion models alone, but you can show another thing that I love about the mathematicians. They always say you can show something. You can actually turn this elbow into these three parts. The first one is that we have for the first step, so the conditional likelihood. We have the last step, so at the very end. And then we have this in the middle. It is like average over t and over noise. And this is what we do actually here. This is what we are interested in. And how diffusion models work is that you have some neural network that tries to predict this noise that you just added at one single step. So like this super small step, we have a neural network that will try to revert it back. All right? And now, because of that, we don't need to, and because of these two distributions that we showed before, instead of doing this 1,000 steps sequentially, we can just pick somewhere at random this t, because we know how to jump from x to zt, right? And so that's why training is getting very simple. It's like you just sample t, you sample noise, you sample zt. This is this one distribution q of zt given x. And then you predict this noise and calculate the update, period. Okay? And why we can do that? Again, because like by making many, many steps, we optimize the correct objective, right? The full elbow, right? Yeah, and also here is this lambda. If we set it to 1, this is the simple loss. And this is the paper that I mentioned earlier. Jonathan and Ho, they published in 2020. So like 5 years after Yasha. And this was like the huge breakthrough. Since then, like everyone uses diffusion processes, diffusion models, sorry. Cool. So this is in a nutshell. Here is some example. Oh, actually, I forgot to add the reference. This is from my paper. So this is like, okay. So we have this, we use this joint model, joint diffusion model that we trained on, among others, these malaria cells. And here we show how these visual counterfactuals work. So we take some forward process, we take some like these cells with parasite and without parasite, and then, or the other way around. We add 20% of noise, we flip the label, and we apply the backwards diffusion. And as you can see, so let's say here, we have this, or here are this with this parasite, here without. And after applying diffusion and flipping it, you can see the prediction changes at some point. Now the process gives us from this unhealthy to healthy cells and the other way around, healthy to unhealthy, right? And why this is fantastic is that we never told any information about what this unhealthy means. So the model only saw images and labels, 0 and 1, right? And now by flipping the label, the model removed this parasite or added this parasite, so these purple dots, right? So this is quite interesting that from super weak labels or super weak information, not very like informative, just one single bit, the model learned to somehow generate this proper, let's say, images. Cool. So this is about diffusion models. And here is a super short note about energy-based models that Martin was so excited about. So energy-based models are, you can say, the ultimate models. And why? Because you can basically define so-called energy function, and you, for free, let's say, you can calculate the distribution. It's called Boltzmann or Gibbs distribution, all right? So it's always defined the same way. So it's e to the power of minus energy function divided by the partition function, where the partition function is the normalizing constant that sums over all possible states. Straight away, this is the problem why energy-based models are not so widely used, because calculating this normalizing constant is, of course, hard. Why? Summing over all states, crazy hard, right? But why this is so cool? Because again, now we turn modeling distributions into modeling energy functions. That could be nice. Yesterday, I remember some posters. They were also this, oh, we have some energy, right? Some potential function, whatever. You can have in physics, in chemistry, you can have these energy functions straight away. You can immediately turn into distributions. You can play with these energies. You can add or subtract whatever you want. You can also define these energy functions for free. For instance, here, something that I used to work quite a lot, like 10 years ago, restricted Boltzmann machines, so we can define very particular energy function. But in general, modern energy-based models, so the energy function is just a neural network, right? And we train it. So we train a neural network to give us not parameters of a distribution, but that it gives us the energy of given state, right? Also nice, if you are like familiar with the exponential family of distributions, this is exactly also connected to that. Cool. All right. So this was about this, concludes this first part. Any question or quick comment? Cool. All right. So now I'm going to walk you through some, I have time till 1 o'clock, right? All right. So perfect. I think I should be ready a bit faster, but let's see. All right. So now about what we can do with these models, right? And now I'm going to give you like different examples. Some examples won't be about this probabilistic model that I just mentioned, all right? So there will be like some dissonance, let's say, because I told you about deep generative models, but I will show you some also differential equations. But I do it on purpose because I want you to realize that, first of all, this general Gen AI could be really, if whenever you think of some generative process, so it actually fits this generative AI, right? So, but also I want you to see that you can use really different aspects, all right? And what I'm going to do also is that I want to highlight some problems that are maybe a bit less interesting to the general public, but they are super important, and if you ever work with chemistry or drug discovery, so I think you will appreciate that, I hope. That actually, oh, these points are also like AI doable, let's say, all right? Cool. So yes, how can we use this generative AI in drug discovery? So here, a quick reminder, I will put different models somewhere on this triangle, and I didn't mention earlier, but every time I say something about models, I really think about probabilistic distributions in explicit or implicit way, right? So explicit, namely, I really think about Gaussian or something like that, or implicit in the way that my model, even if it's a set of differential equations, it really defines some distribution for me, okay? And these three aspects that I actually really appreciated from the paper from recursion is that to think about this explain, discover, and predict, right? Because in our case, in drug discovery, these are the important aspects, let's say, these angles that we look at these different models. All right. So first, something about these conditional distributions. So again, so we had this nice discussion during the lunch break, the coffee break. Like Martin asked me, like, why generative, not probabilistic? And again, this is something like, I would say really, in some sense, maybe following the hype, right? Because everything is generative these days because it's cool. But also that I would say that it is also for historical reasons that whenever you think about this generative process, this is your generative model, all right? So it is really, of course, about sampling data, but you can sample data in many different ways. And also, to me, like this distinction that something is discriminative, it's really weird these days because, for instance, all LLMs are conditional models. And also, there are plenty of papers that use LLMs to classify something, right? You give some text, you describe something, and you ask, okay, what is the label for that? And this LLM gives you some label. Is it generative or discriminative? My answer is, who cares what's the label for that, right? As long as it works, as long as we understand what's going on, it's fine. But maybe it helps to say generative, that we are about this process. But here, I will give you some example of actually these purely discriminative models. But I want you to realize that if we actually get some distribution of, for instance, molecules, you can turn it immediately into a generative process. Okay? Or you can use these models to drive your drive training of your generative process. Okay? So this is something like in the movie Inception, that somehow you start thinking after this meeting, I hope, that everything is about generating processes. Okay? So this is the idea. All right. So here is the first example. And when I say the problem is about predicting the dimensional structure, so probably you already know what is coming in the next slide, right? Can you predict what's going to happen? What I'm going to talk about? Yes, AlphaFold, exactly. So the point here is that there was this CASP competition, right? Very famous one, that actually had a set of different sub-challenges that were very difficult for many years. And then this community, they started solving them one by one, and every year they added new competitions, right? Some new proteins, and so it was, I think this is one of the best examples of computational sciences in general, that actually the community created these challenges that were solved incrementally, because this is, I think, the best way of making progress. And then, of course, DeepMind came into the game, and they said, we solved it. Even though I think with AlphaFold, it's one of the biggest breakthroughs in AI, right? Not necessarily in computational chemistry, because there are these other methods that were actually better in some competitions. But of course, DeepMind has very good PR, and also they know how to, let's say, publish. So they really immediately went to Nature, created blog posts, videos, etc., and whatnot. But in all fairness, I would say they did something really cool, right? So in AlphaFold 2, I think Hannes is going to talk about it more. He mentioned yesterday, so I'm going to briefly only mention some things. So here they, for instance, use a lot of, first of all, they used a lot of chemistry, knowledge about chemistry, because how they formulated these deep neural nets. So they used a lot of properties of, for instance, these proteins, right, and structures. One of those that, as far as I remember, they use these equivariant neural networks, because you can, of course, in 3D, you can rotate anything and it's still the same object, right? So they use that. And of course, it's important to mention that, in some sense, AlphaFold was awarded the Nobel Prize. Here, really represented by Demis Hassabis. But this is for, let's say, AlphaFold, right? This Nobel Prize. And then AlphaFold 3, that was published, I think, last year, maybe November-ish or something, somewhere, I think, in the fall. So they actually use a different approach. They have a different model that, as you can see, starts using also diffusion model inside, okay? So in this sense, they have this conditional model. I want to show you these arrows. And you can say that there is this Gaussian blob, and for given some conditioning, this diffusion turns this into this 3D structure, right? So this is actually really cool, and I want you to have a mental note that this will come back, all right? So this is the general idea, and this is how people define it. There's also, I remember one poster yesterday that was about also like about something very similar, right? About materials, I think. So this was really interesting. And now going, so this was actually also I didn't maybe highlighted it. This is really about explaining, right? So this model was used to actually explain. And when I showed before this was this, it fell into this bucket because this is like for given 2D structure, we predict a 3D structure, right? And again, I want to highlight this doesn't need to be always about classification, this conditional distribution, okay? It is really changing one into something else. And this could be, again, generative. And why it is actually very generative in this case is because if you think about it, this Gaussian noise could be turned into something a little bit different structure, okay? Because every time you run it, you will get some noise in this process, and it would generate you something a little bit different, okay? In terms of positions. All right. Now let's look into maybe this P of X and discovering some novel insight through some lab in the loop. So one example is, for instance, about molecule generation. So this is this very standard. If you ever say, hey, I'm using Gen AI in drug discovery, so this will be the first thing that pops to your mind or someone's mind, because this is actually about generating molecules, small molecules. So the whole point is that we have this super gigantic search space, which is very combinatorial, and our goal is to generate novel molecules. In some sense, this is also, you can say, that we try to solve this optimization problem by having some probabilistic model, right? So instead of looking for specific molecules, we try to sample. And there's this very nice connection between sampling and optimization, that actually if you want to sample from this high probability regions, it is almost like equivalent to optimizing the energy function, right? So this is actually really cool. And here's an example that I looked it up for you. This is, I think, one of the first big successes of AI in drug discovery. I don't know if you ever heard about this molecule. I didn't, but it was published in 2021. A Japanese company, they used artificial intelligence to find this drug, and they had this very nice approach that they had this wet lab in the loop, I think, and this was successful because this is one of the few molecules given by an AI system that passed clinical trials, right? At least in the beginning. We don't have too many of these molecules, say AI-generated molecules, passing some clinical trials. And a few comments before we go. So probably know better than me, but molecules can be represented in different ways. So using smiles or selfies or whatnot. There are different of these representations. Like in the AI terms, I would say this is like text, right? We can treat it literally as text, even though it's a bit more tricky than text, but yeah, we can say these are like letters or symbols. Then we have molecular graphs, and we can literally treat them as graphs with nodes having some specific features. Or we can say like 3D representations, so this like some, again, graphs, but a bit more complicated, or even some voxels, right? So we can do it this way. So this is how we just represent molecules. And one of the first like most successful papers published in this space was in 2018, where Rafael Gomez Bombarelli and others, they presented this very nice method that had this variational autoencoder together with a classifier or some property prediction, right? Predictor. So they literally trained this as a joint distribution, And they factorize it in this way, so that we can sample molecules, and once they are sampled, we can predict what's going on there, right? And I want to highlight two things. First, this is a joint model, so this is this really truly generative model. And the second thing is that it was published in 2018. And in my opinion, like, many people after that, they were a bit scared to publish papers that were joined, because like many reviewers probably said, or would have said that this is some incremental work, right? So people started looking into completely different approaches, but in my personal opinion, this is how we should do it. We should train joint models, right? Especially in the chemistry domain. So here we have this P of X being some VAE and autoencoder, and then this is like the predictor. It's literally not only this head, this neural network, but this whole thing, but with shared neural network between VAE and the predictor. And why this is cool? Because once we have this joint distribution, we can use very simple optimization. I think they use this gradient descent. For what we use this optimization? For instance, lead optimization, right? For de novo drug discovery design. So we can literally start looking for such molecules that they optimize some particular properties, right? So in other words, we start wandering in this latent space of molecules, and because we have this predictor, so for every single point, we can always check what is the property that we are looking for. Okay, is it clear? Yeah, and so in many, many papers, this joint distribution is done the other way around. People have P of X given Y, and then P of Y, sorry. And to me, this is a very wrong approach, because we typically have trillion of molecules, and for one particular property, we have maybe one molecule, right, at best. So training in this way is very hard, because what is the guarantee that we really generalize in the property space for which we have molecules? We should do it the other way around, as they did it. All right, so this is one thing. Then we have this P of X trained as an unconditional model using Molgan. And they had this generator, that there is this adjacency tensor, this annotation matrix. So they used, I think, of course, they used molecular graphs, and they generated how different nodes are connected, and then what kind of properties are in the nodes. And then they had these two components, like a discriminator that was looking into, is it a fake or real molecule, and also this reward network that was indicating whether some property is met or not. And this was also published in like 2018. It's a very nice paper. And of course, the first part, they use this laws for, I think, Wasserstein-Gunn, so for generation, and for this reward network for properties, as I mentioned. Another way of looking into molecule generation is about, for instance, using autoregressive models. So if we treat molecules as smiles, right, as I said, so we have symbols. So now we can say that we can start generating molecules token by token, right? So if you're familiar with smiles, this is not the smartest way to do, because smiles, actually the bracket and so on, so they are not sequential, right? But, well, if you are an AI arrogant researcher, you can say, who cares, they will learn. And actually, maybe the sad part of that is that actually they learn to generate these molecules. And why the sad part is because, well, again, it is a clear violation of the representation. It is a clear violation of causality. yet they can generate very, very well, right? And so my colleagues in Eindhoven, so they had this LSTM model they used successfully in many papers. And here is this very new, published in 2024 in the fall, this idea of using XLSTM. So our colleagues in Linz, led by Sepp Hochreiter, the LSTM person, right? They propose this XLSTM, a new architecture, and they use it with Ginter Klambauer. They use it for generating smiles in this bio XLSTM. Among other things, they also had for proteins, for DNA, and what else? Modeling. Yeah, so this is in general. So they had these 3 cases, and for chemistry, for drug discovery, they use this. And they even show that they compare it with different other architectures, like Mamba or transformers, and they show, of course, that they are better. Otherwise, they wouldn't have a paper, right? So they had to show that it works better. But honestly, I think this is a very interesting architecture and very interesting model. Like when I look at these blobs, I never see anything interesting, but they highlighted that there is something nice. Cool. And here is a project that I was involved in, but actually led by Adam Izdebski when he came to me to Eindhoven, and we started it some time ago. And he continued that at Helmholtz with Eva Szczurek and others. And the idea is to have this joint model that actually uses a transformer backbone, right? And here is this that we have input tokens, and we have 2 heads, let's say, at the end of this transformer. And one is for token probabilities, so to really generate smiles, or to predict the property, right? And this model is now quite, like, I would say weird, because we have one single neural network, everything is the same, and depending on the task we are in, whether we want to predict or we want to generate, we change the mask of the attention. If we want to generate, we have this causal mask, so we ensure that the process is truly autoregressive. But when we have the prediction mask, we have the prediction task, we have the full mask. So it means that the attention looks at the whole input at once, right? At first, when Adam came to me with this idea that we can share these transformers, I told him that it won't work, but why not? You can try it. And then he came after a couple of days and said, you know what, actually it works. So then we started digging further and further and further, and then when the whole team from Warsaw moved to, almost the whole team moved to Munich, so they continued, and actually they got even better results, and there are some, I personally, I hate when someone shows some tables, because to me it's like, who cares? I don't see anything I can follow. But here I am showing it because this is for a very nice application, this antimicrobial peptide design. And first we can show that actually we can generate very nicely, but also we can look into the attention mechanism. So this is like a byproduct of the transformer-based backbone. We can start analyzing what these attention masks look at, and you can see that they start highlighting some aspects of these peptides. So we can start analyzing them as well. So some sort of explainability there, all right? Right, so this is about autoregressive models, and here about diffusion models, because before we looked at smiles mainly with some maybe molecular graphs, and here we look at 3D structures. So really represented as positions. And now if we think about it in this way, so diffusion models maybe have make a lot of sense, because now we have these positions and we can really start as some blob, And then the diffusion process maybe should start putting these atoms in correct places, right? And in such a way, you can think now that before in these images, we are just adding a little bit of noise such that this pure noise starts looking as some object and eventually we get an object. Here we have something very similar. We have this Gaussian blob. We start moving these atoms that eventually we get a structure. One big challenge here was to avoid generating the same molecule, treating the same molecule as different if we rotate it. Because of course in 3D you immediately get into this problem that of course if I start rotating it is the same object, but how these pure stupid neural nets know that this is the same object? We can equip them with equivariance. So it means that if I rotate my object, these neural networks, they internal representations, they're rotated in the same way, right? So this is equivariance. And my colleagues at the University of Amsterdam, Emil Hocheboom and Victor Satoras Garcia, they proposed this method that actually used equivariant, I think, graph neural nets, if I remember properly, to have exactly this property. And here we see this, how it works. So equivariance is that if we start with blob and rotate it and then apply diffusion, it's exactly the same as first applying diffusion and then rotating it. Is it clear? Cool. And this was something like a really nice paper that actually sparked a lot of attention in this domain because people were able to publish a lot of papers by, for instance, changing it from unconditional to conditional and so on, right? So this was from their original paper again to say, to show what I explained in words, that this pure blob, starts looking like a molecule, and after some time, there you go, you get a molecule, right? So this is the idea, and here's like this process again as a static representation, right? So this is the unconditional model. When I was preparing these slides, I found this paper, very interesting paper, that has this conditional model, that we have this 3D molecule, but we also have some 3D molecule seed. So in other words, we can use it for de novo drug design. So we get some, maybe our heat, and now we want to look for some leads. I'm saying it correct? Yes, correct way, right? Yes. So then we can use that, and the whole point is how to guide or how to control this generation by having information about this original like seed molecule, and they used in this case invariant graph neural network. And I'm using this equivariant and invariant not to mess with your heads, but to highlight what is the difference. Like equivariant is that whenever I rotate or do something with my object, the same happens to my internal representation of a neural network. Invariant means that no matter what I do with my object, I always get the same as my internal representation or as my output. So if I let's say for one molecule in 3D I get 0.7, if I rotate this molecule, I all the time get 0.7. It's called invariance. All right? So here, does it make sense that they had to use invariant graph neural network instead of equivariant? I hope you get it, because you want to control, you want to steer this generative process. Okay? Right, another very nice example, and this is from NVIDIA, GenMol, published, I think maybe February this year. And what they did, it is like a model that generates smiles for given condition. This condition could be none, so it could be just unconditional model, okay? And I'm showing it for two reasons. Why is that they use discrete diffusion model. So this was a model that generates everything at once. And instead of now adding Gaussian noise, they have a categorical distribution. So for these smiles, you can imagine, I think it's, maybe you don't see it very well, but they start with nothing or something a little bit. And then step by step, similarly to Gaussian noise, you start seeing that these symbols, they start popping up in some order, okay, in some random order. And this is like, from steps to step, this smiles occurs magically, right, in the end. So this is the process, and then they use it for de novo drag design, some linker generation, scaffold morphing, motif extension, and so on, so on. So this was the idea of why they called it a generalist, because it is one model that fits so many different tasks, right? And another thing is that by having one single model, you can now start using different data sets for different tasks, and you still have one single architecture for that, one single model. So you can start using this, the transferability in some way. Okay, and here is a nice representation. What is the difference between autoregressive model and a diffusion model? Is that in this autoregressive model, we start adding step by step more and more tokens. And here we have, let's say, all tokens at once, and in this one big process, multiple steps, we generate everything at once. Cool. This is work that you will listen to, I think, more during the next. So this is like this DiffDoc. This is for using diffusion models for molecular docking. Very nice work. So I'm going to skip it for the sake of time. And now I would like to, any question? So this is really about this drug design, but in terms of small molecules, right? Now I would like to show you, if you still have power before the lunch break. I hope you do. I will throw some different aspects, some different tasks at you. Hopefully you will resonate with them. So, but some tasks that are, I think, less popular than others, like at least this molecule generation. So now let's look at the joint distribution, and not necessarily we always have distribution, as I said. So one example I want to share again from my research. So, for instance, we want to understand regulatory mechanisms of diseases. So there's this very nice example that I keep in mind, that, for instance, lack of vitamin B12 can cause like anemia and even some changes in your DNA synthesis, right? You know way more than me, but in general, as far as I remember, this is this very nice example that we need some vitamins to regulate our mechanisms, right? So we can, of course, we can try to understand some mechanisms in our bodies in this way of looking into what happens if we have too much of some compound or too little, right? And this is very, very hard to figure out, and many weird things may happen. And so what we did is that we proposed this pipeline, that we have this exactly this joint model with this generative AI with some predictor. We prepared this platform that we're able to generate and predict to have some surrogate model for selecting such compounds that are somehow interesting to us. Then, of course, it is not enough. So that's why I like this example and I always give it, because basically AI ends here in some sense, and then the standard approaches have to kick in. So for instance, this some drug filters that we know. There's this synthesizability, or how it's called, like whether some molecule can be synthesized or not, right? So this is super important. Many people say that who cares about AI? What really matters is if I can do it or not, because what if you give me some molecule that is impossible or no one knows how to do that? Then another 10 years or 20 years to figure out how to do that. And of course, docking as another level of filtering, let's say, because we want to know whether this molecule would fit or not, right? It could be, this docking could be part of that step, but sometimes it's just simply very hard. And here we decided to do it at the end, that once we have filtered set of candidates, then we can really, one by one, we can inspect it with human experts. And so it turned into some leads for further steps. Now, to look into the same joint models, but about predicting some responses to therapies or to some external factors. So here's one thing that I was also involved in, so in enzyme kinetics, so in general, how enzymes react, and so on, so on. So this is this very well-known model called Michaelis-Menten model. I don't know if you heard about it, but probably, yeah, I see people not. So yes, so I'm very happy to hear that. And this will be not this very typical generative model and very typical application of generative models, but again, we can put it under the umbrella of generative AI, because here generation was the key. And the point is that we have this very nice, simple model representing some reactions, right? And we are interested in values of this Michaelis, I think it's, how it's called, Michaelis constant, I think, and this KCAT. And we want to find them. And the typical approach is that in a wet lab, you do a lot of measurements. Then you use this plot, you create this plot, you do curve fitting, and then you read some values from this plot, and this is how you get these constants. And the main disadvantage here is that to get these measurements, once you get these measurements, milliseconds and you get everything. But to get this measurement, it could be like weeks of work, if not months, right? A lot of work and wasted energy, etc. So we pose this problem in a different way. We said, like, what if we get one single measurement? Can we now do, like, let's say, can we figure out these values from this one single measurement? And in some sense, figure out everything else by computations. And we use this idea of so-called simulation-based inference, or this approximate Bayesian computation, that we try to figure out what is the posterior of these parameters from this one single measurement, having this simulator in the form of Michaelis-Menten model. All right? So if you are familiar with this simulation-based inference, basically super boring, because you can think of maybe some new models or methods. But from this application perspective, I find it super interesting, right? And to me, very surprisingly, it worked out very well. And we use it in this project for when COVID kicked in. And we actually used that. We had like fewer measurements, and then we simulated everything. And we got some parameters that actually fit very well to measurements, and we were able to approximate these parameters, right, for COVID and SARS-CoV-1. And I also want to highlight it, not to brag, but to actually show that thanks to this computational method, we were able to be super fast and quick, right? So we put this the first draft on bioRxiv 2 months after the first infections in the Netherlands. All right? So to me, this is to showcase the power of generative AI and computational methods. Right? So what I showed you in the very beginning, hey, you can shorten it from X years to, I don't know, 2 years or 1 year. This is the example, all right? And it is really possible to do. Right. Now let's take a look at this P of y given x again. And so here we predicted by looking at that, and now we are looking at this conditional. And for instance, there is another very interesting aspect of phenotypic profiling, and this mechanism of action, for instance, also very important, right, for drug discovery. So now we are looking again at completely different modality. Before we looked at molecules, then something like proteins, molecules, maybe some just signals, some measurements. Now we look at images. And there is, for instance, this one very nice, very well-known data set of microscopy images about mechanisms of action from the Broad Institute. And with my colleagues from Helmholtz Munich, so we developed this model. I promise no equations, but here are a few equations. But we developed this model that predicted this mechanism of action, for instance, through some Bayesian method, right? And the whole point was that how we can use information about, let's say, multiple cells to predict one single mechanism of action, all right? So what we did, or also we had this application of single-cell RNA-seq, and how we can predict something, right, based on having multiple single cells, right? So immediately we can think of multiple applications, clinical applications, and for R&D purposes. And so the whole point was that we know that there's a lot of uncertainty, and our uncertainty estimation was very important to us. So we use this Bayesian method with some variational posteriors, so variational inference. And the whole point was from this so-called mixed models, how to use this information from multiple input objects. And we used this attention-based pooling, so we had some attention mechanism, and we used pre-trained embedding models, some foundation models, to get embeddings. And that being said, this is for single-cell data. Unfortunately, I think this is for, maybe this is also for this mechanism of action. Sorry, this is also for the mechanism of action to show, again, the numbers are not super important, but what is important is that we're surpassing this magical level of 90%, right? When you get above 90%, so people start paying attention. So this is something like important to mention. And also, because this is this attention-based model, we can look into the attention mechanism or attention maps, and we can start looking which of those cells were picked by our model to predict the mechanism of action, right? And so if we can look at those, so there are some baseline methods, so like top-weighted, bottom-weighted, so you can see that, oh, actually, here are cells, but in our method, what happened is that this top were all cells, but the least weighted are basically about the background, which is something that we would expect, right? So we want our method to really understand what's going on, that some cells are cells and background are not treated as something interesting, right? So this is to brag about a little bit. It's a really cool project, led by Jan Engelman and Alessandro Palma. It was really cool. And so now, again, if we look at these joint models, so here another example from my background. backyard, sorry. So this is like we have, for instance, some general mathematical model. We can call it a simulator. How we can use this idea of generating something here. So we looked at baker's yeast and well-studied glycolytic pathway model for that. And our problem was the following. Like, can we, having this model and very limited data, can we actually predict what's going on inside? And the example is very simple. So imagine that we have these differential equations defining the whole model, right? So, but in the reality, we can only measure input and outputs, right? We can't measure everything what's going on internally, unless we really start interfering with these living cells, right? So, for instance, I inject some amount of glucose, and then I observe how much is left, or some I always forget substrate. No, products. So what kind of products I see, right? But what's going on internally, I can't really measure, right? Because this is inside cells. So this was the problem statement in our case. And we use this so-called population-based optimization methods that are actually very generative in nature, that we start looking into, we start generating possible solutions. And then we look at this simulator and we see which of those should survive or should die, right? In the optimization process. So now we are like doing like, we have this population of individuals and we progress. And to my personal surprise, this was all in silico, by the way. We didn't have real measurements. This was everything simulated. So this is this pinch of salt that you should take. But we had this joint model that we really had a surrogate model that predicted which are good or bad, and this model that we developed some years ago to actually generate these potential solutions. And when we combine this, so we had really this P of X and Y, eventually this approach was capable of finding such values of internal parameters that actually when we took these parameters and we compared it with the, let's say, real measurements, everything simulated again. So we were able to see also for all this internal unobserved. So you can see that actually which one, red is real, blue is predicted, and shade is 3 times standard deviation. So basically it really worked extremely well for some, I don't remember now how many seeds, but there were like maybe 10 or so. So this was to me very surprising that we are capable of really finding the truth, let's say, and we can find these parameters. And why this is interesting is because you can imagine that you have a model of a cell, and now you have a healthy cell. You want to figure out everything what's going on in this cell. So you want to find the parameter values. And then you have, for instance, cancer cells. And again, you want to figure out what's going on in this whole cell, right? So having some measurements, we can figure out parameters again, and we can see, oh, actually this maybe process is odd, and this is our potential target. Right. And now, at the end, I want to highlight a few also very cool, very recent applications. So really about this joint model again, and about everything here. So about explaining, discovering, predicting, and whatnot, right? And here, this is like this molecular science with something that if you go to San Francisco or the Bay Area and you attend completely some meetup at random about AI, you will hear about agents, all right? Like agents are everywhere in the virtual world, digital world, not in the real world, I hope. But so they are really everywhere, and they are super, like everyone invests in agents in Silicon Valley. And here is one example that honestly I'm super like my mind is blown by this. Okay, so there is this foundation non-profit called Future House AI, and they like 1 month ago, less than 1 month ago, they published this technical report about ITER Zero. So they have this reasoning model for chemistry, right? So this is like this big LLM that takes prompts and answers your questions. And here I think I have at least a few examples. Yeah, so for instance, this is interesting. So identify a plausible chemical compounds with this formula, and you can see that their methods worked well, and O3 or Opus 4, so entropic, they failed. Or they ask some question, and ITER provided reasoning, and you can, I think they have this, that you can also see what is in the reasoning process, okay? And they provided something that was not trained on. And in general, it really works very well. The idea of this future house AI, the idea is to create this agent scientist, right? This AI-based scientist that can generate hypotheses, evaluate them, reason about them, and communicate with a human scientist, right? So this is a step further towards that. The company by itself, it's very interesting because they also have wet labs. I think one of the co-founders is a computational chemist or even chemist. So it's not like yet another AI group of people that want to solve chemistry without knowing what they're doing. It's really a company that is led by chemists. So this is really, I think, if you are interested in such topics, so go and check their website. It's really interesting. And also there are many papers, this positioning papers that highlight that, hey, we should use LLMs together with generative models and whatnot in creating these systems and creating this agent that can communicate with scientists and can help with R&D processes. Here is another, like some example from Cell journal from last year, I think November or October. It's also quite new. And interestingly enough, like many things that they mentioned, let's say 1 year ago, nowadays we can see these systems that they pop up, right? So this is really cool. And they of course highlight that, I think here as well. Yeah, so here is like this, for instance, also for experimental design. So I also heard that this story is somewhere that people ask about some protocols, right? Or provided they protocols, and these agents were able to spot some potential issues and suggested some modifications, and they really then even, I think, try to put ChatGPT or something as a co-author, and then journal rejected the request or something like that. But it's very interesting what's going on, and I think that like 1-2 years ago, many people were pretty skeptical about using AI or these LLMs in their research. I think nowadays it's standard, right? I know how many of you have used these LLMs in your research, right? Yeah, me too, actually. It's like, so yeah, it's very interesting to see. And also one final note on that, on the agentic AI. I personally, I was very skeptical for a long time. I'm still quite skeptical because this real idea behind these agents, it's, I think, really challenging, and it touches upon really AGI, whatever it is. But right now, what people do is they really think about agents in terms of this software development 2.0 in some sense. So to many companies and startups, this is really like not only following the hype, Don't get me wrong. It's not like, oh, let's do agents because it's hyped. Not really. But they assume that whatever comes from AI systems or AI, like when they import some library and they just call some object, they assume that this is deterministic, right? But actually, these Gen AI methods are far from being deterministic. And I'm not even talking about hallucinations, but really they can give you multiple different answers, right? But from the software development perspective, they assume these are deterministic. And this is actually quite problematic if you think about it, because it's very hard to verify what's going to happen or to predict what's going to happen with your with the outcome of your software, right? So yeah, this is something that I keep in mind. That's why I'm still a little bit like, I have some problems with this agentic AI for now, if we look at it from the software development perspective. All right, some conclusions and then some questions. Perfect. So one thing I want to highlight as the first point is that Gen AI is way more than LLMs. And as long as LLMs are so hyped, I will keep repeating that. Because like to many people, when I say, oh, I work on generative models, they immediately ask me about LLMs, and this is not the same, right? But I think it's also fair to say that, yeah, generative AI is so popular because and thanks to LLMs, right? So they are part of this big umbrella term. I'm really enthusiastic about computational methods for chemistry and for biology. In my opinion, this is a great, it gives us this synergistic effect that we can even predict fully, because also it shortens our time and our efforts, right? So in my opinion, this is really, really great that we are living in these times that we can see how quickly we can do stuff. Again, generative AI goes beyond only generating drugs or molecular docking or 3D structures. Like almost like literally every single step in your process probably can benefit from AI. So I am very optimistic with respect to that. And so to be more concrete, so yes, understanding biochemical mechanisms, using data, plus maybe symbolic information, right? Pharmacokinetics, dynamics, mechanism of action, enzyme kinetics, many, many more. And for sure, like I work at Chan Zuckerberg Initiative, so I should highlight it very strongly that, of course, digital cells, because this is in our mission and our roadmap. But in my opinion, it is really the next step. So if we can somehow combine all these different models such that we get these digital cells, right? So then we can probably even speed up many discoveries further, right? Because having like generating literally millions of hypotheses and then going through some digital cell or whatever, so we can then be more like optimized, let's say, for wet lab. Right? So this is super interesting, in my opinion. And that's it. And now I'm really looking forward to questions. Oh, thanks.
Many thanks, Jakub.
Thank you.
I hope that your wide description would influence the process of generating of ideas and questions of our participants. Do we have any?
Hey, thanks for the talk. It was
Thank you.
great. I wanted to ask you about generating out of distribution and whether there is any chance that generative models will discover any new biology, or will be just going around confirming stuff that biologists and chemists knew for a very long time.
Right, perfect. It's a very, very good question. It's multi-layered even. I think there are many aspects to that. So first of all, like out of distribution, I would say we are still not very good at providing models that are good at detecting out of distributions. This is the first. So this is the first big problem. The second is that out of distribution is a little bit unclear. Like we more or less can define it, but it's very hard to solve it in some sense, because like, are we as human beings good at out of distribution? Like we explore, and that's why we get new data and we move forward. So with respect to that, I am quite positive that actually this is maybe not a problem. Like the problem is to detect what is out of distribution, detect which parts of our search space are with low probability, such that we can get some observations there. So yeah, so this would be my answer. We are not very good at detecting out of distribution, but if we are not out of distribution, it's actually something that we desire. And I think that another positive answer would be that from this vast amount of data we have access to, and we can process these days, for us, it is already out of our limits, right? So, like, even there was a nice poster yesterday about patents, like analyzing patents. So, for instance, right now for us, there was a very beautiful example. Now, I don't remember the exact names, but I think from 2 days we can get to half of a day. So, without AI, this would be impossible, right? We still would be like spending a lot of time. So because of that, maybe going to these regions that, or realizing something out of current distribution will be possible, because we would say, even as human beings, oh, it's impossible to look there, but AI will indicate, because there are some maybe potential aspects. Cool, thank you. Oh yeah, we have here in the, or maybe in the back. Oh. I know.
Yeah.
Yeah.
Thanks for the talk. It was
Thank you.
awesome. I noted down so many papers that I want to check out afterwards.
Great.
But one of the themes that kind of kept reoccurring was this theme of symmetries and equivariance and invariance. And maybe this is a slightly controversial question, but even you mentioned, AlphaFold 2 and then AlphaFold 3. AlphaFold 2 made an effort to put like equivariance in this, like, this block that actually generates U structures. Then AlphaFold 3 had the diffusion model, like you said, no equivariance.
Right.
So do you think moving forward, this is something that we should be paying attention to, because it makes the model slightly more complicated usually,
right.
like trying to incorporate equivariance or invariance? Or do you think it's all like scaling laws and, bigger models, more data, more compute, and we don't need to worry about the symmetry stuff?
Right. So I will first, thank you very much. So this is a very good question. So I will rephrase it a bit. So that, is it really necessary to have this inductive biases, very strong ones? Because it's like, this is probably not even a $1 million, but $1 billion question. So I will I will answer with some anecdote. I remember I listened to Taco Cohen, who is one of the basically main figures in this equivariant neural net world. I listened to his talk, and he presented, by the way, he's like an uber nerd, but also super funny guy. And his presentation was as follows. He first presented like 20 slides how awesome equivariant neural nets are and what great results you can get. And then the last slide was some very recent paper at that time that didn't use equivariant neural nets, used more data, and got better results. So is it something satisfactory? I don't think so. I still believe that having in this Bayesian way of thinking, if we have a good prior, we should get a better posterior. And in some sense, if we know that, for instance, rotations are important, why not to use this knowledge and to like implement it directly? The problem is that in many cases, in most of the cases, we don't know what is the good inductive bias. So we don't know if actually rotations it's enough. Of course not. So yeah, so I would say yes and no. If we can get this prior knowledge, great, let's use it. If not, let's take more data. But also I want to add something, because if we go exactly beyond equivariance and we really focus on inductive biases, and for instance, one of problems that I keep in mind and I don't see a solution yet is, for instance, we have books, right, with tons of knowledge. And right now, how we can incorporate this knowledge into a model by reading these books, so LLMs go through these books. But it's not actually what I think, this is not definitely how we learn, because we don't learn by being trained by parts or chunks. Well, sometimes, but typically we just gather knowledge in some sense. And to me, this would be very interesting to see how to combine this very symbolic knowledge with these very non-symbolic models. To me, this is still an open question. I'm not convinced that LLMs going through books, it's the same. I mean something different. I think this process, it's not there yet. This would be very interesting. And this touches upon these inductive biases, right? Cool, thank you. Very good question.
Okay, I have quite similar one. Because you said that equivariance is sensible to use, but the quite similar but slightly different question is whether is it going to be used in the future in practice? Because I believe it was first introduced for images, and there was a hype for that. However, it was quite complicated, and it was easily replaceable by data augmentation, and I don't think it's now used in image modality. So do you think the same future is reserved for equivariance in 3D molecule generation?
So as a scientist, I would say I really don't know, because as of today, it's way less popular, but who knows? Maybe there will be something new that is some equivariant neural net that it's super duper and we will use it again. The other thing is that, like, I will answer a little bit differently. So, for instance, current trends are that transformers at this point, they seem to be very powerful, and also, like, even for visual computer vision, we can still patch our images up, and we can process them using transformers. And to some degree, transformers have this permutation equivariance. You can shuffle, but then we do this positional encoding and so on. So yeah, I don't know. Maybe it is less important to have this equivariance explicitly hard-coded. Maybe it's more important to have some model that is somehow constrained, yet very flexible, and it figures it out by itself. This I don't know, right? So yeah, I really don't know. But also, I would say I want to highlight one thing. If we can get, whoever in this room has a problem, and this problem can be very well defined, and we can introduce some structure into this problem, we can inject some inductive biases, please do that. Don't use transformers because everyone uses that. If you can define your problem and it's solvable by k nearest neighbors, good for you.
You just killed 99% of science, I think.
You have a second question? No? Oh, okay. So it was one. Okay, perfect. Cool, thank you.
Just maybe not to question, but to comment on this, on your question. So in computer vision, actually, convolutional neural networks are still very good, especially when there is not enough data for transformance. And there you have this bias because they shift invariant or equivariant, so it's used there, and they are even probably better than transformers, exactly in the situations where you don't have not countable amount of the data. So I think it is important to use these invariances. And it is used in computer vision until now.
And I will add to this comment. It's a brilliant comment, because this is exactly about the amount of data in some sense. It's again about having, like in this Bayesian way of thinking, priors and posteriors. If you have not enough data, whatever it means, the stronger your prior is, the better for you. And exactly, like, yeah, don't throw away convolutional neural nets, because they are very useful. And also transformers, there is this very well-known fact that actually if you don't have enough data, again, whatever it means, they suck. But once you get more and more and more, they start scaling up, right? So yeah, thanks. This is a very good comment.
But I think equivalence is slightly different, because you can always generate data that should be treated by the model as the same data points. Yeah, you can rotate the image, for instance. So the lack of data is not an issue, I guess. Maybe computational power is.
Okay, so this is a good reply, and this is actually what happened in this anecdote I gave with Taco. Because, for instance, if you know precisely that rotations are good, so then you can start rotating by data augmentation. But I don't want to delve into this discussion too much, because I'm not very strong at equivariant neural nets, and maybe actually people from equivariant neural nets, they have some specific answer, I don't know. But maybe this could be better, I don't know.
Okay, thanks.
Thank you.
I have one more question, actually connected to the very first question in this round. About the discovering the novel knowledge, novel science. Are generative models good at this topic? I mean, like, we need some exploration, some reinforcement learning based or search across the hypothesis spaces. Are the current generative models capable of doing this, or we really need to stick to MCMC-based approaches?
Right, very good question, thank you. I would say that probably the answer is no, they are not very good at that. And in my opinion, the answer is the following. Again, now I will use the blackboard again because it will be easier for me to answer it instead of waving hands. But it won't be math, no worries. So, like, we have the following. We have this, and I will use these diagrams well known for reinforcement learning. So we have environment, and we have our model, right? Right now, what happens is that we get data from the environment, and that's it. We train the model, and then it is like deployed, and it just works. But there's never this feedback loop, basically, because in terms of training, right? It is trained, period. But actually, in my opinion, to answer your question, we really need this to be like a solid line, that we have this constant, somehow that this model can make some actions, get data, and figure out further. There must be this feedback loop, and with training and everything, right? So it's also not the same as, because someone may say that, oh, but we have LLMs, and they communicate, but they don't retrain, right? People now figure out to have like millions of tokens in the context window, but it's still not that the weights are updated, right? And I mean that really to have this real progress, we need to retrain, be able to retrain all the time.
Okay, thanks. But I think that you do not need actually retraining.
Maybe.
For example, when you have like work in AI scientist, you can have a bag with sentences that are true statements, and kind of a LAM operating upon this, and then you are just adding the new observation or new knowledge base of the new observation to your bag of true statements, and then you can operate. It's like updating your prior.
Sure. Yeah,
this,
so
yeah.
I'm not saying that this is not possible. I'm saying that right now, I don't see a satisfactory result for that.
Okay, thanks.